why your name tags are very important, and your tent cards are extremely important. This is how someone can look at you and call on you if you have a question. I'm noting that I am taking off my name tag right now, not because I am assuming you all know who I am, but because I will be moving and the jangling will sound a little weird on Zoom. I'm going to get into the lecture in just a second, but I realize that I sort of have the floor at the moment, and I wanted to talk a little bit about supervised models, which has been the theme that we've been discussing today. It'll be the theme more or less for the remainder of the week. And I'm going to re-emphasize a point that was brought up earlier by Juliana, which is that you should think hard whether or not machine learning is actually needed for the problem at hand. I think there's a lot of excitement, not for bad reasons. There is a lot of incredible things that are happening right now as various forms of applications of machine learning. So there should be a lot of excitement, but I see a lot of people running to use machine learning for problems where it is absolutely not necessary. And we are about to move in the lectures that we are doing into extremely more complicated models than everything that we have discussed so far. And it's going to get very complicated by the time we get to the end of the week. So what I do, and I'm just posing this as an exercise for all of you as you think about whether or not you might want to start adapting machine learning techniques in your own research, is I make the students that are working in my group try to find a solution to the problem that they are working on that does not use machine learning at all. And only once that fails do we start talking about what is the machine learning model that we can apply. I think this accomplishes two important goals. One is that, as I said, there's many instances there was a choice, which means there's a bias, right? And there's things we can do to try to minimize the effects of those biases. But as soon as you make that choice, you are biased. Whatever the stars are over here, you cannot see when you're looking over here, right? So digging into your data deeply will give you insights into what might be the fault points in the models that you build. And this is also hugely important. In the future, if you're ever lucky enough to have me as an anonymous referee, and you build a machine learning model, that will be the first question you get asked in the referee report. Where are the areas where your model could fail? It is disappointing how often people have no idea what the answer to that question is. Okay, so those are my quick thoughts on supervised learning. And now I'll be talking about a specific type of supervised learning, a new model, an additional model to the ones that we learned about earlier today, called the Perceptron. And in some respects, this is a talk that's going to set up our transition into talking about neural networks, which is going to be the focus for the remainder of the week. This notebook, we'll be doing live coding. So there are some slides. I will talk when there are slides, and then we'll get to code blocks, and I will stop and ask all of you to work on the code. So if you haven't done a Git pull, please do that. And you can wait a few minutes, but very soon we're going to have everybody open up and start working on the notebook once we get there. I'll also know that this is a new machine, and the most recent version of Jupyter is a little bit buggy when you do slideshows. So if something weird happens, we'll get it fixed, but there may be a couple hiccups as we go through the slides. All right. Consider the following image. What do you see? Take a moment to discuss with your partner. I'm kidding, I'm kidding, I'm kidding. Okay? That was the number 8. You all knew that was the number 8. You didn't have to think even for a microsecond to understand that that was the number 8. Okay, so now for the actual question. Given everything you've learned thus far this session, I want you to think about how would you build a random forest algorithm, or to simplify it, it can be a decision tree. That's fine too. For a binary classifier that will separate the number 8 from any other handwritten number. Right? Take a moment to discuss that with your partner. Brian, are you recording right now?
Can't do it directly. But like, if it doesn't know, it's awesome. maybe round, like identifying the circular shape, because that's depending on what font you use, 3, 8, 6, 9. That's it. Maybe 2 if you're weird, but like. But do you remember? Do you remember so do you remember there
You know, I know what I'm doing.
Yeah, is that
was that for TC? Was that yeah. They figured out that divided by 3 find the version in the small friction
or like 6?
just like in general where
I think those work.
I think
Right.
oh. So using like a tree, precision tree, like maybe making something that you notice.
Let's wrap up in the next 30 seconds or so.
A round thing. Maybe round is better. There are less things in like a number set. Right. Sorry. Like a 1, 7, 4, 5. Yeah. Well, then we can.
All right,
just have
let's
another
wrap
one.
up.
Where they would be in relationship to one another.
All right. Would anyone like to share back with us ways that you might be able to classify number 8, the random forest model? Yoki?
So we discussed using the geometry or like the morphology of the number itself. Also, where there are gaps, the top and bottom portion. So yeah, the morphology I think would be the feature that we want to use.
Okay. How would you get that feature?
So you're asking how we get the feature of the different.
So you mentioned morphology.
Yeah.
So I agree, that'd be great. Let's measure the morphology. I'm asking now, how do we measure that morphology? Because we have to put that into the random forest. We can't just say random forest, use morphology.
Yeah. So I suppose it would be at the pixel level you would want to see, you know, as you move along the image of the number, how do the pixels occupied change?
Okay, so yeah, so you look at some kind of change in the pixels,
Yeah.
and maybe you get a feature that way. Other thoughts? Dan?
We had 2 ideas.
Okay.
For 2 tracing through a circle. I don't know the circle is close.
Uh-huh.
2 circles.
Okay.
Then we noted that the top circle kind of doesn't close here. So Ash had the idea of for an S and a backwards S.
Okay. Uh-huh. So basically, specifically pulling out things, morphological features that correspond to 8-ness, whatever that means. Okay. Other ideas? Anai?
Was discussing, we thought, why not make it a decision tree that first you decide whether or not the number has, like the image has a circle.
Uh-huh.
Then if it has a circle, then you have like four numbers that could potentially be classified in that, and then you make another like branch of the tree that says does it have two circles? And would potentially give us 8.
Okay.
But I was just thinking about the graphs that were made in the morning where we vertically and horizontally tried splitting them.
Mm-hmm.
So if we were to say if we split across the center, horizontally across the center, how we could get one circle.
Okay. So yeah, so a few ideas similar to what we said before, but also discussion of what if we segment the image and we look for specific things in the different segments that would correspond to different numbers. Yeah, these are all great ideas. I heard other people saying similar things. I have a few possible approaches. Again, there's more or less an infinite number here, but we could build some algorithm that identifies circles, right? For example, the number 3, which might be easily confused with the number 8, does not in fact have any fully closed circles, right? We could build some algorithm that identifies lines. So 8 is mostly curved, although some people do a pretty strong slash as part of their 8. Okay, but 4 has no curves at all, typically. We could examine only the bottom half of the image. This gets at the segmentation idea because an 8 and a 9 look very similar in the top, but they look very different in the bottom. So we could do these things. Writing these algorithms would be pretty hard though, right? When I said, how do you actually do this? Maybe some of you have some ideas. I actually don't know. Find a circle. That's a very broad and complex statement to just hand over to a computer, right? I don't know what the for loop is that actually accomplishes that goal. So, and as we've said, we've only discussed a few features, which will all be very complex. And everything we've discussed so far, it's not totally clear to me that that would still allow us to separate 8 and 0. No, someone said 2 circles. I take it back. 2 circles, yes, that would separate 8 and 0. The things I said would not obviously separate 8 and 0. Okay. So we're on the road to success, but if you're looking at the image 8, all of you instantly knew you saw the image 8. And that's because each of you has a supercomputer in between your ears. And the supercomputer has been trained over many, 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 many generations of human evolution so that you can immediately recognize things that you see. But writing down rules, which is what's required for all of the types of supervised learning that we have discussed so far this session, we have to write down rules that give us numbers that can then go into things like k-means or a decision tree. And making these rules precise is really, really difficult. And so for complex tasks like computer vision or classifying handwritten digits, ultimately what we need is a new type of machine learning. And this has been the revolution that has occurred over the last decade, and literally only a decade. This is not like people were doing this 20 years ago, right, in the last decade. And that revolution is building and using neural nets, which will be the topic of tomorrow and the following days. Today, we're going to talk about a building block to get towards a neural net. And so for that, I want to talk about the Perceptron, which is a single artificial neuron. I apologize, like I said, this is a little buggy. So some of the text is getting cut off, but it should be on all of your screens if you open up the notebook. To be clear, I'm not a biologist, so I will give you a very simplified version for how we think biologically the brain works. And that is that you have a whole bunch of neurons in your brain, and those neurons all have many inputs. For several of the neurons, the input is other neurons, but this can also be different receptors that are in your body. Right? I know that I am touching my palm right now that's because there are signals traveling from my skin somehow, I'm not a biologist, up to my brain, making neurons fire. That's telling me I am touching my palm. Any individual neuron is taking its various inputs, looking at their relative intensity. I'm waving my hands a lot here on purpose. And then deciding, oh, this is something that matters, or this is something that does not matter. And so either the neurons light up as you propagate through the chain of neurons and other inputs, or they stay dormant. I am not worried, my brain is not worried that a saber-toothed tiger has bitten my leg right now, because that's not happening, right? I have those neurons in my brain. If a saber-toothed tiger was to bite my leg, I would become immediately very worried. But I am not worried about that right now. So those neurons, that combination of neurons, is dormant. So that's our very simple picture. So I want to talk about the perceptron, which was inspired by this idea, which may not even be correct for how biology works, which is something that people say, like in the news all the time. Neural networks work just like the human brain. No, we don't actually know how the human brain works. But these ideas were inspired by our thoughts for how the brain might work. So how does a perceptron work? It takes several different binary inputs. We'll call them, that did not render right at all. Well, that should be x1, x2 through x sub n. So these are our inputs. And ultimately, this will produce a single binary output. So either the perceptron turns on or it stays off. Each input has a relevant weight, W1, W2 through W sub n. And what we do is we multiply the weights by the corresponding inputs before taking the sum of all of those, right? So the sum of the weighted inputs, and comparing this to some threshold. So if my sum is greater than the threshold, my perceptron turns on. The threshold is here and the sum is here, the perceptron remains off. It's the basic structure. This is what I just said, sorry. But if it turns on the output, because this is all computers, the output is 1. Okay. If it remains deactivated, the output is 0. So here's a graphical representation of what this looks like. So here we have a whole bunch of different inputs, x sub I through, in this case, indexed by m, multiplied by the weight. This all goes into the neuron. A sum is taken, and you get the output, which is either 1 or 0. Mathematically, this looks like this. I warned you that it was buggy. So the output is 0 again if you have the sum of the weights and the inputs less than the threshold. It's 1 if you're greater than the threshold. So a single perceptron can then be used to answer questions that rely on many varied inputs. We're about to work through a relatively simple example. Okay. So what if you consider the question, should I walk the dog? I see a lot of confused people. If you have a pet dog, just like you, a human, the dog will need to go to the bathroom, ideally not inside your house. So when the dog needs to go to the bathroom, it's a good idea to walk the dog. That's where this question comes from, right? Okay, so to answer that question, should I walk the dog? We might ask several other questions that have binary answers. Is it raining? It's never fun to go outside when it's raining. Is the dog asleep? Is it a good idea to wake up a dog that is currently sleeping? Has it been more than 6 hours since the dog last went outside? If yes, maybe we should take the dog outside so that it can go to the bathroom. Right? Okay. So we want some binary output that just tells us, yes, take the dog for a walk, or no, you can stay inside and relax. And that's going to come from, in this case, 3 different binary inputs for those 3 questions that we just asked. And we're going to build a perceptron to answer this particular question. You're secretly thinking, do we really need a perceptron to do that? The answer is no. We're starting here. We're going to build to something more complex. Okay? So I'd like to ask you all to write a function called walkDog that acts as a perceptron to decide whether or not you should walk the dog. And the function will take in 3 arguments, a tuple, with the binary answer to your 3 questions. So that's your input. An optional tuple with relative weights for each input. And then an optional threshold for which the default value is going to be equal to 2.5. So here we have that function, and I'm now going to ask you to work through this. So I'm sharing here a solution. This is not the only solution, and I could easily write 10 different versions of this, not just changing the text. But we have our inputs, top of our model questions. We have our weights. We want our weights to have a default argument. So this is why we say in the call here that weights is equal to this particular array. What that means is that that's the default, but when we call this particular function, we are allowed to input whatever weights we want. You didn't realize that this is how this is done. You have all seen this before because this happens with things like a plot in Matplotlib, right? What symbol is used, that is the default, but you are of course able to override that at any point in time. So that's what that means. Same thing for threshold, which we're just going to set equal to an integer in this case of 2.5. As another quick aside, if you have not seen this before, there's a little bit of information right here after I write the definition of my function that I'm creating in Python. This is what is called docstrings. It is possible that if you learn nothing else from me during the DSFP, that building the habits to always write docstrings might be the most valuable thing you learn. And this will feel like extra effort. And you will convince yourself that you can remember everything you have ever done before in the past. But you cannot. You will not. At some point, you'll write some software. You won't touch it for 6 months. And then you'll wonder what in the world is going on here. Docstrings are a pretty low overhead way to provide yourself with more information. If you've looked at the documentation for anything in Python, it's all docstrings. And there's some ways that you can render this that looks nice, which is when you get to things like read the docs, and we'll talk about things like that in the future. But at the very least, if you're writing docstrings, you should just say, what are the things that go into this function? And what are the things that come out? And then in a quick 30 seconds, you can always remind yourself what it is that what you've written does. All right. We typically try to do a good job of putting docstrings into the notebooks. You can tell when Brian and I are very tired because there aren't docstrings in our notebooks. Okay. All right. Anyway, that's what that is. That's what's there. But as I said, all we have to do is we have to take the sum of the questions multiplied by the weights and compare that to the threshold. If it's greater than that, then we want to go for the walk. Walk is a Boolean, so we want walk to be equal to true. If it's less than the threshold, walk should be false. So we should be able to execute that. And I might mostly avoid the slideshow since it wasn't working particularly well. So next, we ask, using the newly created Perceptron to determine, use the new Perceptron to determine if you should walk the dog if the following is true. It is raining, the dog is asleep, and the dog last went out 2.5 hours ago. So that would mean that the answers to our questions are, it is raining, so that is true. The dog is asleep, so that is also true. And the dog last went out 2.5 hours ago, which is less than, I don't remember what number I used, but it's less than whatever that number is. So 110. And we can stop there because, again, we've created defaults for the weights and the threshold. All right, so let's run that. You may safely watch another episode of Stranger Things. You do not have to walk the dog right now. Okay. Again, we don't really need a perceptron. If it's raining and the dog is asleep, I think you know that you don't need to walk the dog. But let's say that it's been 4 more hours. It is still raining, but the dog wakes up. Now should you walk the dog? So our input in this case is, what was the first question? It's raining. We don't want to go for a walk. The dog is awake. That's a 0. And it's been more than 6.5 hours. So 1, 0, 1 is our input. If we run that, we see do not delay. Dog needs to use the bathroom. Right? Okay. I'm gonna see if for the slide part the slides work, but it's clear that the coding is not gonna work in the slide format. So this will be a little janky. My apologies. All right, so now I want to talk about a generic perceptron. We can simplify the way that we just put things together by replacing the sum with a dot product. So instead, we're just going to take the dot product of W sub n and X sub n, and we're going to move the threshold to the other side of the equation. And we're going to call this something new. We're going to call it the bias P. And so now our output is just going to be the dot product of the weights with the input plus the bias or minus the bias. It doesn't matter. It'll get fixed later, right? So you might see it either way if you're looking at different papers, and compare that to 0. And if that dot product plus the bias is less than 0, your output is 0. If it's greater than 0, your output is 1. So now what I would like to ask you to do is to build a generic perceptron that can take any collection of input signals and weights and a bias, and then determine the binary output from that artificial neuron. This says the same thing. We want this function to return a Boolean, so either true if the perceptron has been activated, or false if it has not. One second, true.
Why you are not directly saying summation, like the sum of the weighted and the input? Like why you are mentioning the dot product? You didn't mention the dot product.
I'm just saying that it's a way to slightly simplify the notation, which makes it more consistent with what you will find in the literature.
It is.
Is not dot. Okay.
Well, it's also in your notebook. You should also be able to just scroll up, right? But you want to see this. Had just a moment ago. In fact, if you wanted to be pretty snarky, you could say it's identical to the thing we did before, because we didn't actually specify that there's only 3 questions for the dog walking problem. But we're inputting some signals and some weights. We can just check by taking the dot product of the signals of the weights, adding the bias, check if it's greater than 0 or less than or equal to 0, and that tells us whether or not to return true or false. So we have a generic perceptron function now. And then for the next 2 problems, we can test some various inputs. So we have a signal of 2.3, 5.3, 1.2, 3.4. And we have weights of -3, 2, 0.5, and -1. And we have a bias that is equal to 0. So we are just asking if these are the signals and the weights. Is this particular perceptron activated? So we can execute that cell. And we forgot to execute this cell. defining the perceptron function, we can execute that cell and we see yes. In this particular instance, perceptron has been activated. We can ask the same thing. Let's keep the signals and the weights the same, but let's change the bias to be -2. So I'm just doing a copy paste, swapping -2 for that 0. We ask, is this thing activated? Now the answer is false. Right. Okay. So now I want to talk about how one might be able to use a perceptron in order to perform classification. I just said this, but perceptrons can be used for binary classification problems. That part is important, okay? The things we learned about earlier today, you can do a many class problem. With k nearest neighbors, you can find quasars, galaxies, and stars. With our single perceptron, you are either activated, i.e. true, or deactivated false. So that is one distinction. We can only do binary classification, 2-class problems here. So to demonstrate how this works, we're going to just build a very generic synthetic 2-dimensional data set. But everything we do as part of this example can be scaled to higher dimensions. The only limitation really is the binary classification. To start, we're going to use scikit-learn, and we're going to make this fake data set. So this just means we're going to execute this particular cell. Now I have to jump back again. Now you're unhappy? No, oh, you just went to the end. Okay. Wait, where are we?
Right there.
Okay, so we execute this first thing. This make blobs, I won't go into it in a lot of detail, but it makes random data. It essentially is assuming different Gaussian distributions in whatever number of dimensions you give it. We're limiting ourselves to 2 dimensions in this case. We can plot this data very quickly. Not plot this data very quickly. We can fix this. First rule of live coding, never live code. Okay. Let's see, we need to redefine our perceptrons. That will matter. And we should be able to make our blobs. We can get rid of that. This plot should work now. Okay, all right, so here's our data. 2 variables, x1, x2. Somewhat clustered, but also clearly some overlap, right? This thing is over here with all the other circles. This circle's over here with all the other plus symbols. Okay. So this is what we're going to try to classify now. All right, back to the slides. Again, my apologies that this is not a little cleaner. I'm sure that I hate it more than you do. Okay. So how can we use a perceptron to classify this particular 2-dimensional data set? We have 2 inputs, so there'll be 2 weights. We'll also need to determine a bias. And all of that together will determine whether or not the perceptron has been activated. But the difference relative to the quick examples we looked at earlier is that we have 30 different observations that we can use to train our algorithm. So for a perceptron, training means that you update the weights. So we don't just set the weights. We don't just say W is equal to this. We start with W equal to something, and then we make small changes to W to try and get better results. So the pseudocode looks something like this. You apply the perceptron to all of the data. You then adjust the weights. If the perceptron makes some incorrect classification, you then repeat this for all of your individual data points. And then you do this sort of looping over all of the data a total number of times that is set by you, the user, which we're going to call here M. So we basically say, this data point goes into the perceptron. Is it correct? If it's not correct, change the weights a little bit. Do it for the next data point. Do it for the next data point. So all the data points, and then we do it again. So we're just going to be slowly adjusting the weights to try to make our perceptron become more accurate. Right? So how do we adjust the weights? For every single sample, we can evaluate the model error. And in this particular case, for binary classification, that's as simple as just saying, is it right or is it wrong? And then we try to change the weight, again, slightly, so that we can reduce the error in the proper direction. So like if we're well below the threshold, but the answer is that the neuron should be activated for the source, we want the weight to increase a lot so that the input is more likely to trigger activation. Okay? All right. So in order to figure out how do we update the weights, here's mathematically how we do that. You, similar to the lecture we saw a moment ago, define something called the learning rate eta, and you just take your current weight, you multiply and then you add to that the learning rate multiplied by the difference between the true value and what was predicted, multiplied by your input signal. Was there a question? Sorry, I thought I heard. Okay. So that learning rate is going to determine how quickly W is changing, how quickly the weights are changing. As a quick caveat, if we make that some huge number, what will happen is you're going to test the model on one data point and then wildly change W because eta is huge. Then you test it on the next thing and it's like, oh, we super overcorrected. And then you jump back the other way. Okay, so there's tuning that needs to happen here. If eta is really large, you'll kind of just be bouncing back and forth without ever getting closer to the answer. If eta is super duper, super small, you will advance towards the answer very, very slowly. This will come up tomorrow and in the days after as well. Okay, so there's some tuning that has to happen with that eta. But otherwise, all you're doing is making a small adjustment weight to try to get closer to classifying your answers correctly. Theo, sorry. The question is, why do you multiply by the signal? And the signal is part of what gives you the magnitude of how close you are to the threshold. So the signal, now I'm worried I didn't explicitly state this. In the first example, I said that the signal is always answer to a binary question. I did not say this. Okay, so thank you for asking this question. In problem 1, we said that it's always a binary question that you're asking. So X is either always 1 or 0. But we are making this slightly more generic and allowing non-binary inputs now, which we did in problem 2 and we'll be doing moving forward. And so knowing the magnitude of the signal affects how much you want to move your weight towards getting closer to being at the threshold, if that's what's desired, or below the threshold. That's why you multiply by X. Sabina? The question is this relation always linear? For the perceptron, yes. Yes. Okay. I mentioned this briefly, but the learning rate is something that is selected by the user. You may be wondering, how in the world do I pick this? Just as you probably were wondering, how in the world do I pick K for K nearest neighbors? And the solution is typically cross-validation. So run some cross-validation, you can figure out a learning rate that is very appropriate. So to train the perceptron, we also need to decide the total number of iterations, which we're calling M, that we're going to pass through the training data. These iterations are called epochs. So we're going to say, if we say we want to loop through all of the data 20 times, we're going to run the model for 20 epochs. Within each epoch, the weights and the bias are being updated in order to improve the predictions that we make. So here's the big one. We're going to take what we've done so far. We're going to put it together to actually classify sources. So I want you to write a function that's called train perceptron. The input for this is going to be X. That's a feature array, similar to what we used yesterday for unsupervised clustering and what you use today. There's also going to be Y. That's the labels, which in this case is just 0 and 1. There will be weights, bias, epochs, and a learning rate. And so we want to run through all the data for M epochs, and during each epoch, update the weights and the bias using the equation that was given a few slides before. Question?
Bias in that equation.
Bias is not. Being a little lazy in my wording there. You can optimize by changing both. We're actually only going to adjust the weights. Yeah, that's the short answer. So I should change that. I should say that we're only updating the weights for this problem. Another question.
So why is a binary not like a value? Have three.
Y is the actual answers,
Okay.
which we have, and that comes from the cell a little bit higher in the notebook where we made the blobs and plotted the data set.
And then the Y predicted is that the output. So is that signals times plus T, or is it that additional?
So you have your input that'll go into the function we've already written called perceptron, and the Y predicted is just the output from that.
Store that information somewhere. Let's call it little x.
This one's going to take a while, so Brian and I will be walking around. We'll answer questions.
No, that's not. First is an integer. So maybe
Yeah.
Let's do Or I don't really keep track of that.
Adam, the size of weights is gonna be the size of label, or the size of weights is gonna be the size of the.
Weights is going to, so you have your input signal, features.
Yeah.
So you have two features, so the weights also needs to be
Two.
Same.
two.
It's gonna be something.
Gonna do that.
Yeah, you
Check. Okay. Some empty value.
I would.
Number. I'm gonna set it to 0. And then I'm gonna do is not 0.
When I do
No. And
but yours, like yours.
this is gonna be.
I just feel.
That looks real, maybe? This. Would we want it to return the weights, like the new one?
Yeah. Or you can. No, you don't need to. But you need to use that updated weight in the next step. And then get the finer one.
Yeah. But once it's done doing that, I guess then how does the
Doing the
Perceptron remember that those are the weights?
Using
after
that
it's done
weight.
being trained. Did we say? I don't know. I'm just gonna watch it and just say. Are they separate? Oh, it's just at the end. So I guess it doesn't have to be every. Oh yeah. It doesn't have to be in here. We're done. No. This is for every. Okay. Oh, no. This goes out here.
It does feel like that way.
Yes.
Yeah,
There we
exactly. When something works.
And then you stay in there. Okay. I think that's real. I believe. I believe.
Oh wow. Well, I believe.
Maybe it'll return. Or maybe I'll keep it outside instead. I'll just say, hey, it's or just ask it to return. I don't want to mess with the way that the notebook is structured. If I need it for other things and it's giving stuff back in places that it should. That's gonna update that. That's done. Do that.
Should I find the number one specifications?
Either way, so it doesn't matter.
Let's just do a print station. It's also never hurt anybody, right?
perceptron.
Index does not match any determinant values. Easy. What is? Oh. Oh, small number. Oh, no. Oh, it's the other way. Nope, still mad. Oh, I'm silly. You only take 2 arguments? Quit being so fussy. I guess I can just index it. Objects cannot be interpreted as linear. Wait, what?
Mine is very weird. Like that. Just the weight, like negative.
Is it right?
Is it right?
Maybe.
All right. I'll ask that everyone brings their attention back up here. I have a solution, not the only solution, and possibly not even a correct solution. I literally was typing this out just like the rest of you were. So I'm going to walk through this, and then if any of you catch a bug, let me know, but we'll try to run this in just a second. So I noted that it can be useful to track the misclassification rate, and mainly that's just so that we can see what's happening as we go through the different epochs as part of training this particular model. We don't specify, oh, well, I take it back. Because I did this a little bit lazy, I just made this an empty list. Wait. No, we don't return anything. We don't even need that. Okay, sorry, that can go away. All right, so I don't want to destroy whatever I started with, so I'm just going to recast what we called weights as W sub now, which which is going to be a proxy for our weights as we keep updating them. By doing this, it means that I don't destroy my initial conditions if I want. Again, doesn't matter for this problem, but maybe not a bad idea. To start, I look at how the weights that we start with, how many things are misclassified. So that's all this first loop is. So we're looping over each individual source's features, the capital X, and their labels. We're getting a prediction based on what the weights are. If the prediction is wrong, then we say that we have misclassified a source. That's a problem that needs to be fixed. Here. Otherwise, this number is just going to increment to nonsensical things. So we need to set that equal to 0, and we need to do the same right here. So we're just counting how many things are wrong, and then we're just saying the misclassification rate is whatever percentage it is. So next comes the actual learning. So we're going to loop over the number of epochs that is input to the function. And then we're going to do something very similar, which is that we're going to produce a prediction for every single source within the set. So that's what this loop is doing. But now, instead of just tracking if we've misclassified the thing or not, we're going to update the weights. So that's what this line is here. To hopefully improve the overall classification. So this is the equation we had before. So the new weight, based on whatever the source is based on the old weights plus the learning rate multiplied by the difference and the input signal. Other thing I realized for the question about why we multiply by X is that that's the only way we ensure that the size is the same. Okay, and then we say, okay, now the weights or whatever the updated weights were. I tried to make this very explicit here. You don't actually need 2 lines to accomplish this particular operation. So we do that loop over every source. Then once we've updated the weights, we again ask how many things are misclassified, and we print that out at the end of every epoch. Right? Okay. I'm going to try to execute this. Hopefully it's not unhappy. All right. Currently not unhappy, but the real unhappiness will be here. Okay, so now we want to train the perceptron. We've created X and Y. We then need weights, which we're going to do as 0.1 and 1, a bias of 0, 20 epochs, and a learning rate of 0.05. First rule of live coding, never live code. Who thinks this is going to work? I don't. Thank you all for believing in me. Okay. All right. So I think this means this has worked, but we find that our initial weights of 0.1 and 1, we misclassify almost half of everything. Our learning rate in this case is clearly quite small because we do 1 epoch where we update the weights, and we're still misclassifying 46% of things. And then we update the weights again, and we're misclassifying 46%. And then we misclassify things, and we get to 50%, 53. Well, this is not good. 60. Oh, 63. And then it gets better for a little bit, and then it sort of seems to settle in at around 50% or so. What does this mean? This might mean that there's a bug, because this is not what I was expecting for this particular answer. But really what this means, so this means either there is a bug, or what this means is that our learning rate is too large. So what's happening is we're updating our weights, but we're sort of overshooting the correct answer. Let's see. All right, so the next thing was just adjust stuff, change inputs, and see if things look different. So if what I just said is correct, if we change the learning rate to instead be 0.001, I don't think we'll get as much noise. But again, there may be a bug. Okay, there's not much noise, but things are moving in the wrong direction. Did anyone see what they thought was a bug? And to all of you that believed in me, I apologize for letting you down.
The redefinition of the misclassification of 0 helps.
So we change the weights and we say misclassified as none. And then we run through everything with our updated weights. And if it's wrong, we say that it's misclassified. So I think that is okay.
I don't feel comfortable with including the signal. It's just and if the
Wait.
signal is 0, that's the information that you update with weights.
If the signal is 0, that should provide an update. Yes, but also if your signal is 0, this is why you may want to simultaneously adjust your bias as well. Because then if your signal is 0, you wait. No, I need to think about that part. What?
If your signal is 0, your weight will be
Yes. Yes, that's right. And so then you would need to change the bias. Yeah, so you need to change, if your signal is 0, you would need to change the bias, which we did not do to make things more simple in this example. I still have a little bit of time. Okay, hold on, let me see.
What it's worth, we're getting the exact same answer.
Yeah, I'm getting some of that.
Yes. Yes. Just my weights. This is just what I'm using to count my misclassifiers. And then I put X and Y together so that I can index them in the same notation.
In the solutions that I wrote, I did adjust the bias.
Okay.
And I think that's part of why we're not sort of moving,
And then I just did it.
for the most part, uniformly
Fastest
towards
one, X.
superior results.
I'm just
3 minutes. I can type this in 3 minutes.
data point. I just wanted this notation to match. So it's N and then Y true.
So I clearly made a mistake, and I told you
I got this.
not to
And then I say this and I check to see if it's different. I add it to my counter.
update the bias, and that was wrong, and I didn't give you an equation for that either.
Oh, you can.
All right, actually, it doesn't make sense for me to type this.
Why this one? This one is not working right now, but I just put it.
All right, here. I will finish on time, I promise. Here's the solution that I wrote in the solutions, which looks very similar. So we're updating our weights. We're looking at updated bias. We're counting how many things are misclassified. We do a first loop to figure out, in this case, accuracy, whatever, 6 of one, half dozen of the other. And then we run our epochs, and this all looks very similar. It's not exactly the same, but very similar to what we had a moment ago. But then the last step, which we did not have, and I think that's part of the noise that was introduced, is that we can update the bias in the same way. So we say that the new bias is equal to the old bias plus the learning rate multiplied by the number of things that are correct. So if we've gotten the source correct, we don't change the bias. If we got the source incorrect, we change the bias. It's the same idea to changing the weights. All right, so then when I did that in this example, you can see that eventually I got a model that had an accuracy of 93% for this particular data set. And then you've all seen this, so my joke, but I'm still going to say my joke. In other words, the machine, it is learning. Okay. And then we can adjust things, and by making a very high learning rate, it's actually hard to get adjustments in the model that provide us, our steps are too large, which I've said several times, so I'm not going to hinder on that. This last point is important, so I do want to say I'm not going to finish on time. I am a liar. But this last thing is very important, so I do need to say this, okay? All right, so we've built a perceptron, but we've also seen that there are limitations to the perceptron, okay? And generically, the strength of machine learning, the reason why we want to use machine learning solutions is in order to capture nonlinear behavior within data. But the perceptron is almost too nonlinear. Anytime you have some output that is close to your activation boundary, you make a tiny change in your weights or a tiny change in your bias, and all of a sudden you've totally flipped the classification. So there's basically a magic point, and when you're close to that magic point, you can oscillate very wildly about the answer that you want. So it would be better, our model would be better, this picture for how we could classify things would be better if we actually introduced more gradual changes. Not as soon as we cross a single boundary, we totally flip what we claim that we have found. And so there are other types of artificial neurons that can be used to do this. And I want you to consider for a second the sigmoid function, which is just 1 over 1 plus exponential to the negative z, where z is just the number we were given to our definition of our activation for the perceptron, weights multiplied by signal, and then I flip the sign, it doesn't matter. It can be plus b or minus b, that doesn't matter, okay? And to see this difference, you can look at what these two functions, you can look at how these two functions differ, which I have in this plot here. Okay. So like I was saying, if you're sitting right here with a perceptron and then you change the weights just a tiny bit, all of a sudden your answer dramatically changes to being on versus being off. Whereas with the sigmoid, we have this smooth function. If we change the weights a little bit, we start to creep up or we start to creep down, but we don't have this wholesale dramatic change. And in this way, we're able to take our small steps and get closer and closer to optimal in terms of learning and classification, than we are with the step function, which we were using as part of our perceptron. And in fact, you could even just go into your, it's not a perceptron technically anymore, but you could go in and replace this sigmoid function, and you would do much better than the different examples we did in terms of classifying that simple data set that we have. Okay. How about, I'm sorry, we're 4 minutes over. That is all I have. I will take questions, but I know we're at the end of the day and people are tired. The group dinner is in an hour. There's information about where it is in the Slack. We do hope that you join us. The DSFP is covering dinner. We will not be covering alcoholic beverages, but we are covering dinner. So we do hope you join us. We'll be in an elevated beer garden with views of the Liberty Bell. Should be quite nice. And if you have questions, I will stick around and answer them. But if you're like, I am done for today, it's perfectly acceptable to leave. We'll see you tomorrow morning. Thank you, everyone.